Hello there. Today we'll be doing number 66 of 150. Oh, damn, that's cool because we're getting there. We're doing all the tries today. This is design and add search word data structure. So in this particular problem, we're just creating a word dictionary and we're trying to see if we can, it's basically a try. We're trying to add a word and see if we can find it later. The difference is that we have a period can represent all like characters. So basically a try would be very helpful here because we're looking at all the options for that particular character. I think looking at a set will be very difficult, as well as a, let's say, a list of lists. Anyways, so here we are. We're doing this. We're doing a try. And one thing to note is that we can't search the way we searched before. I mean, searching before was nice, but we need to do something more every time we see a dot. A dot means that we have to do a recursion, and we have to check every single child and move that. We're checking from that point on for that word. It does for those characters. Can I find those characters from that point on or not? And then keep trying for every single character at that point. So we need depth first search. And so first of all, it sounds like a pretty simple stuff, and you'll see so very soon it is. So class equals try node, and let's create our init function. So self, wonderful stuff. So same old child children equals default dict, and we're gonna throw a try node in there. Very simple stuff, and then self.end, very similar to our previous problem, equals false. Then we can set it up similarly, root equals try node, very simple, and it's going to look for its children. So basically cur equals self.root for let's see, in words, so character in word, so cur equals cur.children of C, and that basically creates and assigns the cur to that particular location with that character at that particular child. So then we just set, once we're done with the loop, we can set cur.end equals true because that is the end of the word, and that's it. And that's it for adding words. So very similar to before. Nothing special here. And here's what's going to happen. So what's going to happen is we need to use define a depth first search, and we need a way to track where we are in the start, we're starting to track, and which try node will we go into. So this is our current try node. Let's call it this root. Okay, so basically very simple stuff. So we need to basically find out what sort of item we're working with. So let's say cur equals root, and then let's look at what item we're working with for let's say I in range of start to the particular length of the word that we're working with. I mean, we could insert this, but doesn't matter. Okay, so let's keep going. So we go from the start to the end of the word, wherever our start is. So if we know that we're doing recursion already, so that helps a lot. So if let's say the C equals the word of I, so if the character is equal to a dot, what happens, and else what happens. So if it's a dot, that means we have to recursively call our DFS call for every single child, in cur.children.values. So we're going to go deep into every single child, so DFS, and we're going to do I+1 because that's where we're going to start from now on, and this is we're going to throw a child in there. So what happens? We're returning a true and false. So if this is true, like just return true. If we've gone through all the childs and we have not been able to get a true, let's return false, because that means this is the end of the line. We have tried everything. We have ran our DFS calls. None of our children return. It was possible to get a possible path. So forget it. Otherwise, let's go through a normal path. Looking through a character, which we did very much earlier. So if was it? Yes. So if what's child C not in the current children. Basically, this particular character is not in our children, then return false. Otherwise, let's keep going. Cur equals cur not children at C, and that's all. And once we get to the end, let's return true, and that's very much similar to our previous problem. So we just added this chunk in. So let's run it. Oh, we have a trinode error. Let's see. They have no children. Really? What? Trinodes have children. What's going on? What line is this? Number 14? What is going on? Did I spelled it wrong? No. Huh. Weird. Is this cur correct? Yes. Weird. Weird. I don't know what's happening. Oh, I see. We did not create the trinode. False. False, 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 false. Huh, let's see what's going on here. Not sure exactly what's going on. I'm not sure exactly. Oh, right. I did not call the DFS call. That's the problem. That's kind of dumb. There we go. All is good. No problem here. Apparently the runtime is really long for some reason nowadays. I guess there are many test cases that were not available back then, and it's a pretty slow process. I guess, yeah, I'm just guessing that there are many test cases. So the runtime is going to be like 16 seconds. Oh no, what happened here? Yeah, we have a problem. So at and add a dot at bat. Oh no, I don't know what's wrong now. Exactly. I don't know how to debug this. This is a very bad error. Let's see. We create the word properly. I don't think that's a problem. That can't be a problem. This DFS call looks good. Everything looks to be as it's supposed to be. looking at all the values and everything, and that's correct as well. Yeah, don't really know. Oh, I see. Because we're just returning true, not the word itself. And so let's try that one more time. I think that was it right there. Yeah, that was that right there, that cur.end, because we found a character that was like not it was a word, but then we did not insert that complete word inside. It's like half a word. But anyways, we did it. 19 seconds. I think this is good enough for interview. Going through all of this code. But it is very slow, surprisingly. I will check the discussion section to see if there's anything more to learn when doing this problem next time. I think we've learned a lot already, and that's good enough for us. I think this backtracking, probably there's some probably dynamic programming approach that maybe solves a lot of this problems and speeds this problem up much more quickly, or something, because there's no way that we're this super slow. We're like 19 seconds in. Anyways, we've learned a lot today about backtracking and how to run a DFS call to check our all options. And when you think backtracking, I probably would think DFS. Anyways, learned a lot, enjoyed the problem, and if you liked the video, please like and subscribe. And if you want more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.